Welcome back to Biochemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In the previous video, we actually looked at how we can actually take chlorophyll, and of course humans don't do this to a very significant extent, but ruminant animals do. They actually intake chlorophyll from consumption of all sorts of vegetation, and their colonic bacteria, that is their microflora in their colon, can actually use this enzyme called chlorophyllase to take this giant chlorophyll molecule and cleave off this tail or side chain. And this tail was actually referred to as phytol. And once we had this phytol, we discussed how it can be processed all the way up to Pristanoyl-CoA, and then it can be run through one round of alpha oxidation. And at the end of alpha oxidation, we have this molecule called pristanoic acid. It has a carboxylic acid right here, which can of course be ligated to coenzyme A, which would generate Pristanoyl-CoA. And I left you with that in that video, and I mentioned that this can really just undergo beta oxidation several times. But actually, we're not going to get, if we do beta oxidation on this, just a bunch of acetyl-CoAs. We'll get some. But what I want to do in this video is more or less actually dissect this pristanoic acid and really more or less predict the products of what we would get if we performed beta oxidation on it. All right. So this molecule up here, this is pristanoic acid ligated to coenzyme A. So it's of course Pristanoyl-CoA. And pretty much we're just going to run this through beta oxidation a bunch of times, and I've got this red line here that's showing where we're splitting it, which bonds we're splitting, and we're going to see what the products are. So this is of course our first round of beta oxidation. Okay, so here's our alpha carbon, here's our beta carbon. We're just going to split the bond right between those. And if we look at the product that comes off, it's actually not acetyl-CoA due to this branch. We would actually have one carbon, 2 carbon, and 3 carbons. So actually the product of the first round of beta oxidation on Pristanoyl-CoA is actually propionyl-CoA or propionyl-CoA, and that has its own separate catabolic pathway, which we have discussed in the previous video, but I'm planning on redoing that and doing a newer, fresh video. All right, so that gets us down to this. Again, we're going to shorten it again by 2 carbons, run it through another round of beta oxidation. In this case, there's just 2 carbons that come off, so in the second round of beta oxidation, this thing is just acetyl-CoA. Let's run it through another round. We're going to split the alpha-beta bond right here, so here's where we split, and this pretty much resembles what we had in the first round. So this 3-carbon fragment that comes off with coenzyme A is, of course, propionyl-CoA. We're going to run this through another round. This will be the 4th round of beta oxidation. We're going to split it right here, and of course we're going to get out acetyl-CoA. That gets us down to this molecule right here. We're going to continue this on the next slide. So, got this right here from the previous slide. Let's run it through another round of beta oxidation. This is round number 5, so we're going to split it right here. And of course, we're going to get off a 3-carbon fragment again. So round 5 yields a propionyl-CoA, propionyl-CoA, however you want to pronounce it. Then let's run it through one more round, the 6th round of beta oxidation. So that's going to split this bond right here, alpha-beta bond, right? So of course, right here, we're going to get off an acetyl-CoA. So I've mentioned that. So round 6 gives us an acetyl-CoA. But what's left? Well, if we look at what's left, it's this molecule right here. This molecule has not been seen yet in any of these other prior rounds of beta oxidation on Pristanoyl-CoA. This molecule is actually what's called isobutyryl-CoA. And we don't run into that very much except for in some cases when you're catabolizing one of the branched chain amino acids. I'd have to look back and see which one it is. I don't have it memorized. But this is not something that's too common to run into. But in any case, let's tally up our net gain from beta oxidation of Pristanoyl-CoA. All right, so if we look at what we got from round 1, here's a propionyl-CoA. I guess we can count those up. We have 1 propionyl-CoA in round 1, another in round 3, and another in round 5. That gives us a net gain of propionyl-CoA. Those will actually go, as I mentioned, into a separate catabolic pathway, which will actually end with the production of succinyl-CoA, which can then go into the citric acid cycle. Then if we look at round 2, this gives us an acetyl-CoA, so did round 4 and round 6. So we get 3 acetyl-CoAs out of this pathway. Of course, acetyl-CoA can also go into the citric acid cycle where it fuels the first step, citrate synthase. Of course, it has a variety of other things it can do as well. But then in round 6, we generate 2 products. There's the acetyl-CoA and, of course, isobutyryl-CoA. So we only get one isobutyryl-CoA. That has its own separate catabolic pathway, which we'll again look at in a separate video. So this right here, this is our net gain from several rounds, that is 6 rounds of beta oxidation on Pristanoyl-CoA, which of course was derived from chlorophyll and subsequent alpha oxidation. Okay, so hopefully that makes sense. The other thing I want to just kind of reiterate in this video, because it's a follow-up to the alpha oxidation video, is that humans really do not perform this process to any significant extent. We can do it, but humans don't really run into a lot of branched chain fatty acids like this. Okay, and that's because branched chain fatty acids are really only found on certain molecules like chlorophyll. And think about where chlorophyll is going to be present. It's going to be present in a lot of plant products, but particularly the leaves. Okay, so grass would have chlorophyll, and yes, things like spinach. Spinach would have, of course, some chlorophyll. Some humans eat a lot more spinach than others, but usually humans are eating other things to satisfy their amino acid needs and so on and so forth. So humans are going to eat a lot less chlorophyll than a lot of other creatures, particularly herbivorous creatures that tend to be ruminant animals like cows, horses, and things like that. Okay, and so those organisms are going to intake a lot more chlorophyll than we would, so they're going to perform this process, so phytol development into Pristanoyl-CoA, and then subsequent alpha oxidation to give pristanoic acid. It's not to say that humans can't do this, but we don't do it significantly because we get a lot more of our nutrients from animal products because we are omnivorous creatures, and then unfortunately a lot of processed foods. Okay? So hopefully this process makes sense to you. This is just a follow-up where we predicted the products of beta oxidation on Pristanoyl-CoA. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you very much.